Welcome back to week 7 of this AutoCAD course, and as a continuation from the previous week, we'll focus on the tolerancing techniques that are applied in the geometric dimensioning and tolerancing. So these 2 weeks, that is the previous and this week, we're focusing on the quality part of the drawing, which will ensure that the product function stays good as per the requirement from the production line till inspection and the final application. So what is tolerancing? So just have a look at these two images. So the top one is a unique painting that is drawn by Mr. Vincent van Gogh, that is the Starry Night. It's unique because there is only one that exists of this kind. Whereas in below, you can see this is a snap from a Logitech mouse that has some standard dimensions that is going to. But the below image, that is the mouse, is a mass-produced object. That is, so many millions of mouse has been produced and consumed, whereas only one artistic painting has been done. So when we go for mass production, how to ensure that the product stays true to its function? So that's where your tolerancing kicks in. So in this real world, nothing is going to be absolute or perfect. There is going to be some amount of variations or differences in the component. So the variations will be determined by what manufacturing capability that you have, and what's the level of inspection, what's the quality of inspection that you have, and what's the capable dimension that it can measure through. So based on that, your tolerancing is going to get controlled. Also, you need to ensure interchangeability between the parts. So previously we have seen that this GD&T came onto scope during the World War II when heavy requirement for interchangeability is. So currently what interchangeability means that once you start using a product and suppose there's a defective part in that assembly, then you call for a replacement of that part, not the entire assembly, right? So that newly machined part that is going to be shipped from the production plant or the service center to you has to have a perfect fit to the existing assembly and still deliver the intended function. So that means all your products that you design and produce need to be interchanged to ensure the life cycle of the product gets continued. So this will ensure that it is suitable for mass production, and it will ensure repairability, and also will ensure commonization, that is, you use the standardized parts across different applications to keep your inventory levels to the lowest, inventory variations to the lowest. So putting all together, this tolerances means the allowed variation in the size and geometry of the part to ensure that you comply to the interchangeability and also ensure you have the sufficient manufacturing capability as well as inspection capability. So it's nothing but the difference between your maximum permissible size to the minimum permissible size. So this band is what you call as a tolerance. So typically if you design a component with a very low tolerance, then it calls for special manufacturing methods. That we'll see for in the upcoming slides. So when you call for special manufacturing methods, so it also increases your cost. So it means that higher the tolerance, lower the cost, and lower the tolerance, that is, the lower the bandwidth, that is, it is very precise, that goes your highest cost. Why? Because this cost involves the production cost, it involves the inspection cost, and also the rejection, that is the failure cost, because you have to own the failures. If suppose a product doesn't clear the given tolerance, it is rejected. That material has to be scrapped. So that is the cost of failure. So all this thing is embedded into your overall cost. So what does this tolerance denotes? It denotes the dimension variation. So thereby it conveys the design intent of the object. Next, it can also be denoted as a general note as a manufacturing method denoted to the entire page. So it's a general note stating that all the components produced in that page, in that drawing, has to comply to certain tolerance band. So it's a global tolerance that is performed to that page. Alternatively, you can also specify in the drawing title or in the tolerance block. It means it will apply to the entire component, entire drawings that are applied to it. So it's called a block tolerance. Because in a typical drawing, it might consist of different pages, each page focusing on separate components. Whereas if you apply to the title block, it means that you are applying to the entire drawing all the components, the entire subsection, assembly, everything. So always keep in mind this tolerancing, the limits of tolerance should be finalized in the design stage itself, considering all the capabilities that you have. What is the manufacturing capability, what is the inspection capability, what is the life cycle of the component, how frequently you have to interchange or service the parts. All these factors need to be figured out in the design stage itself, and this tolerancing must be keyed in. It must not and must never be designated in the production stage. So this is the brief about the tolerance. So now moving forward, like how do you specify this tolerance? So let's go back to this. This is a normal circular element, that is the base element that we are considering, wherein we have to mention what is the base dimension and also means the tolerance. So by mentioning the tolerance, you could recollect it's the allowed variation in the size or the geometry of the part. It means that we need to know what is the maximum permissible size and what is the minimum permissible size. It means that we give a minimum boundary to it and also maximized boundary to it. So it means this circular shaft element can lie anywhere between these two surfaces. So how are we going to control it? How to denote it? There are two different methods by doing it. It means the plus or minus tolerances, or again the plus or minus tolerances specifying in a different methodology. So how do you do that? So first is we call this a bilateral tolerance. So in bilateral tolerance, you mean that your base dimension of 50 units dia of this circular shaft elements can vary between plus or minus 0.005. So if you consider this in mm, this means it's in 5 microns. So it means that this 50 mm dia shaft can vary on the upper side by 5 microns and on the lower side by 5 microns, and it is equally distributed across the base, and hence it's called as a equal bilateral tolerance. The next way is the unequal bilateral tolerance. That is, you specify two-sided tolerance, but they are not equal. So that is, on the upper side it can vary until 5 microns, and on the lower side it can vary until only 2 microns. So this is bilateral tolerance split into equal and unequal. So next what we have is unilateral tolerance. So unilateral tolerance means that you specify the tolerance or allow the variation in only one side, either in the maximum or in the minimum side. If it lies in the maximum side, it means it's a unilateral plus tolerance, whereas if it lies in the minimum side, it's called a unilateral minus tolerance. So moving on, the plus or minus tolerances can also be specified by limits. It means that you define the hard bounded variation with two specifications. So that is called two lines plus limit tolerance. It means that you directly denote what is the upper bound and the lower bound. So here the same unequal bilateral tolerance represented in the plus limits way means that the upper side it is 50 mm with 5 micron dia, and the lower side is 49.998, that is 2 microns for the lower side. So here you define the hard limits. So alternatively, you can also specify the minus limits. It means that the lower side is controlled first and then the higher side. This also we can see by specifying what is the material condition, that's the GD&T modifier that we'll look later. But this is how the minus limits are specified. If in case of minus limits, then the lower side will come on first and then the higher side. So this is the minus or plus limits defined by two lines. Alternatively, they can also be defined by a single line, that is this same tolerance defined in a single line. It means the plus limits in a single line. Likewise, these minus limits specified in a single line considers this. So the same plus or minus tolerances can be defined in different manners. So moving forward, let's see how and what are the different key terms that will help us to designate between the tolerance sizes. So how to specify those tolerance sizes and how to determine what are the interactions between the components. In this figure, there are two major components. So one is your basic shaft, that is a typical shaft, and next you have a hole here. So these two are interacting or interfacing elements. So based on this, several dimensions have been defined. So let's look into one by one. The first thing is the size of the shaft or the size of the hole. So what are the various techniques or terms that are used in this definition of this size? So first is the nominal size. So nominal size means that it's the general identification that is used to refer the shaft. It is expressed in a decimal system of dimensioning. So earlier you could see in the previous slide we had mentioned that the nominal size of the shaft was to be 50 mm in diameter. So that is a general identification or base identification that you use to define the shaft or the hole. So next what we see is the basic size or the basic dimension. So it means this the theoretical size based on which the limits are derived for applying the allowances or tolerances. So there is very subtle difference between nominal size and the basic size. But basic size always refers to the theoretical dimension that can be used, but the nominal size is used to denote the base reference as a general identification technique. So next what we have is the actual size of the component. So this actual size is the final most measurement of the actual part, that is the finished part. After machining, after the production processes is done, what is the output component that you have. So now you have three different variations of the sizes, that is you have the actual size and the base size, and to refer to the component as whole you have the nominal size. Next you define the limits based on the tolerances that you have. So the limits basically determine the extreme possible or permissible sizes that is allowed between the actual size lines. So we call it as a max limit and then a min limit. In max limit, the maximum permissible size that is applied for the basic size. So this 50 mm dia, you refer to the shaft as a 50 mm shaft, that means the nominal shaft. To apply the tolerances you need to have a basic dimension, and this basic dimension is again 50 mm, and for that basic dimension you say that the maximum size that is possible is say 5 microns. So 50 plus 0.05 is going to be your max limit for that shaft. Next, min limit, you compute the minimum most size that is possible for the basic size and then apply to it. So based on your max and min limit, you determine the tolerance zone. Here you can see from the variation, that is the minimum size versus the maximum size for the shaft, this shaded zone denotes your tolerance for this shaft. Likewise, your hole, your upper and the lower limits of the sizes will determine the tolerance zone that is allowed in this hole. So these term what we covered was the size and the limits. So next, for the same image of this shaft and hole, the next key term is the deviation. That is, what is the algebraic difference between the basic size and the hole or shaft size of the actual part. Because earlier we were saying about the limits that are allowed based on a drawing, but here for your deviation we measured with the actual component versus the theoretical component. So for upper deviation we say that the difference between this basic size versus the permitted maximum size that is allowed, and that constitutes your upper deviation of this shaft, and it is denoted by ES in angular bracket for hole and in small letters for shaft. Likewise, for the lower deviation, you consider the algebraic difference between the basic size and the permitted maximum size of the part. So for hole, it is EI in caps in angular bracket, and for shaft it is small letters in EI. So what is the actual deviation? The algebraic difference between the actual measured size versus the basic size. So again, going by the tolerance denotes the limits that you can operate on. The deviation measures what is the deviation that is from the actual component versus the basic component, that is the theoretical component. Next, you classify in base of the fundamental deviation. That means that you either choose between these two deviations, that is you choose between the upper or the lower deviation to define the position of the tolerance zone with reference to the zero line, that is the baseline. So it means that you either choose one of these to control the tolerance zone boundary wherein you have to measure the variation. So by selecting these, you select the fundamental deviation wherein you have to control your part. So as we said, the zero line is going to be the line that is drawn through the top generator of the basic shaft. So it means that the basic shaft, the min shaft, actual shaft and max shaft are all aligned together at the bottom, and a straight line is drawn through the top generator of the basic shaft. Through this line is considered as a theoretical line which has no deviation. So suppose if it's drawn in the horizontal way, all the deviations above the zero line are positive and below are negative. So this is how we designate the positive and negative with respect to zero line. So why there are so many terms like the basic shaft or the basic size and the zero line, all those things, is because we are fixing references from where you are considering the tolerances or the deviation. So these are the key terms that you have to see. What we have seen was the size, the limits, and then now the deviation. So moving on, these features, these terminologies are going to get applied to the features of the object in hand. So what do you mean by feature is that it's a general terminology that is applied to a physical portion of a part. That is, it either refers to a surface or a hole or a slot. So it means that in a component you identify different features and then apply control to it. So what is the feature of size? So it means that this feature of size will refer to a cylindrical or a spherical surface or a set of two opposed elements or opposed parallel surface that is going to get associated with a size dimension. So this is called as a feature of size. So let me repeat it. So this feature of size is going to be a cylindrical or a spherical surface or between two opposed elements or opposed parallel surfaces within which you are associating a size. So based on that you define your features. So this is the feature of size. The next important terminology is your datums. So as we said earlier, you need to have some references from which you can measure the component. So wherein this datum will come into play. So these datums are derived from the datum features. It can be either planes or points or lines or axes. So theoretically, they do not exist at all. They are reference features. So they are completely perfect. That is, they don't have any variation at all. And hence, these datums are used only for simulation purposes. That is, only for references purposes. So these datum feature simulations are commonly used for connecting the origins of measurements for either location or orientation or profile or runout. These are all references to from which the variations are measured or controlled. This datum feature is a part feature that contacts a datum. The datum plane or the feature it's in contact with the datum feature. So let's look into what the datum reference frame is. So datum reference frame elements actually exist within a framework of three mutually perpendicular intersecting planes. So these are the virtual reference frame that will help denote the datums. It means that you define a primary plane, a secondary plane, and a tertiary plane that will call for references from which the datum of the feature are referred to. So this is the use of a datum reference frame. So typically you can call it as your X, Y, Z planes from where you are referencing the datums of those features. So if you could see here, in this primary data plane you have 3 points of minimum contact, whereas in the secondary datum there are 2 points of contact, and in tertiary datum you have 1 point of contact. So based on that you can choose how many reference frames you want to based on your component. So as we said earlier, in order to measure those datum you need to have some planes or datum features that can be used for simulation. So the simulation is going to be accomplished by positioning the specifically identified features of the object in contact with the appropriate datum simulator planes that we have seen earlier in a stated order of precedence, that is, which is first. So based on the order you refer the object, so that you are restricting the motion of the datum reference plane. So these specifically identified features are called as the datum features, that is in association with the simulation features. Let us look by example. If you could see, this is your object, and for that object you define the datum feature that is as the surface of this object. In order to measure the surface of this object, that is the datum feature, you construct an imaginary datum externally that is going to be your datum feature simulator, wherein you measure how the object is going to be here. So for this datum feature and the datum feature simulator, you have a common datum axis by which they are aligned together, so that the final objective is measured. Suppose if we are measuring the maximum allowance or the maximum clearance for this object, then this is how the datum feature simulator is used. This simulator can be emulsified by a component that is typically called as a gauge. So this is a highly controlled component, this gauge, that is used for inspection purposes. So you can call it as a go or no go gauge, wherein suppose if you are measuring the exterior surface and you are controlling using your gauge as an internal component, then this is based on the higher limits. You can qualify this feature as either go or no go and then reject it or approve it. So this is how this datum feature simulation is going to be used to control the limits of your object. So parallelly, this can also be applied to other surface. Suppose if you want to measure how this surface of this object going to behave, then you have to have a reference frame wherein the feature of this surface plate is highly controlled. So from there you can measure the variation of this plate. So this is what is called as a datum feature simulation. So next, associated with the tolerancing is the two terminologies, allowances and clearances. We look into those two. So allowances means that it is defined as the intentional difference that you allow in the components so that the maximum material limits of the mating parts are defined. It means that allowance is the minimum clearance, that is a positive allowance, or a maximum interference, that is negative allowance, between the mating parts. So allowance is calculated by the MMC, that is the maximum material condition of a hole, and the interfacing part, that is the shaft, its most maximum most condition. So in these conditions, what is the intentional difference that you are allowing is called the allowance. So this we'll look into example later stage, but now focusing on the definition for next clearance. This is similar to the allowance, but here you define as the loosest fit, that is the you look for the least most condition of the shaft and the hole, and it will control the loosest fit or the maximum intended difference between the mating parts. So here we have seen two terminologies, that is allowance and clearances. They are used interchangeably based on the type of the assembled objects. So let us look in. So what we have seen is allowances and clearances. These are going to be used for defining the assembly features. So in terms of assembly, we have to mention how well the fit of the components is. So in order to determine the fits of it, let us consider these two examples based on the previous thing. Let us consider that for a given object, for a given hole and a shaft, the maximum tolerance that is allowed is 0.3, and the allowance, that is the maximum mating condition between those two assembling components, that is the shaft and the hole, is 0.2. Do remember, this tolerance is going to get applied for the individual components, whereas the allowance or the clearance is going to apply for the group of components, that is to an assembly. So towards this, we can define the fit of those components in two methodologies, either keeping the hole as the reference, that is the hole basis system, or keeping the shaft as reference as the shaft basis system. So in hole basis system, what we are doing is, the fit is arrived by associating the varying shaft limit dimensions with a single reference hole. That means that the hole dimension is kept as constant, whereas the shaft limits are varied to determine what is the deviations are. And again, so for the single reference hole, the lower deviation, that is the fundamental deviation here, is 0. That is, the minimum limit of the hole is equal to its basic size, which is taken as the base for computing all other limit dimensions. So if you recollect the form, the key terminologies, what we said was, we define the deviations, wherein you can also go for a fundamental deviation, wherein you choose either one of those deviation and apply to the basic size. So here the basic size is going to be your hole, and hence in this hole basis system, your lower deviation is going to be 0, that is the minimum limit of the hole is equal to its maximum size. So let us look with an example here. So we have a hole and a shaft. So as we said, here this hole is going to be as a reference, and hence we are going for the minimum limit of the hole is what is taken as a reference. It's going to be considered as the basic size of the hole. So for this hole of 50 mm dia, the tolerance is 0.3, the maximum tolerance. So assuming this is the lowest size, that is 50.2, so this is going to be the minimum limit of the hole. So with this condition, you apply the tolerance, that is the maximum limit for this hole is going to be 50.5, and then based on this, you arrive with the allowance, that is with the base of this dimension 50.2, you apply the allowance to determine what is going to be your maximum and minimum sizes of your shaft. So it means that for the 50.2, for allowance of 0.2, your shaft is going to have a maximum size of 50, wherein you take in for the lower side, basically from this 50, because it's absolute, you can't consider this dimension at all. So you have assigned the maximum most possible condition of this shaft based on this hole basis system and say it is 50 only, and then you apply the tolerance for this component, that is you allow the variation of 0.3, as you have already specified the max limit of the shaft, so the min limit is going to be 49.7. So this is how your hole basis system is going to act on. So moving forward for the shaft basis system, just you revert the references. So here you consider as a single reference shaft. Based on this, you vary the hole dimensions. And again, for this reference shaft, the upper deviation is going to be 0. That is, the maximum limit of the shaft is going to be equal to its basic size, which is taken as the base for computing all other dimensions. So going by the definition, again the same reference. So for the same dimension, as the shaft is taken as a reference, so this is going to be the reference base condition 50, upon which you apply the tolerance. So this is the maximum size that is allowed. So you go on to the negative side, that is a 0.3 defined as 49.7. So next, based on this definition of 50, that is the maximum limit of the size, then you apply the tolerance, the allowance variation is 0.2, and hence the minimum most size that is allowed for the hole is going to be 50.2, and then applying the tolerance to it is 0.3, that is 50.5. So this is how your hole and shaft basis system is used to applicate the tolerances and the allowances of the assembly so that the intended function of the mating parts is met. So based on these, what are the different types of fits that are allowed? So let us take hole basis system as reference. So here you can see that we have shafts and the hole with the basic size and so on. So there are three different types of fits that are permissible or allowed. That is, we have a clearance fit. So what means by clearance fit is that the largest shaft that is possible is going to be smaller than the smallest hole. That is, consider in this example, the largest possible shaft that is allowed by your definition is going to be still smaller than the smallest hole. So it means that there is going to be a positive allowance here, and it's always greater than 0. So for this shaft, if you see, the largest shaft dimension is going to be 12.48 mm in dia, and the smallest hole is 12.5 mm. So it means that you still have a allowance of 0.02. So this is going to be a clearance fit. So in your shaft basis system, again if you see here, if you are fixing the shaft as the base, and then if you see, the largest shaft is going to be smaller than the smallest hole, and hence the allowance is going to be possible. The terminology is the same, but based on your references, the references of the shaft dia and the hole dia is going to change. So you either stick to the hole basis system or the shaft basis system when you design a component. So next is your transition fit. So in transition fit, it means that the allowance is going to be negative and the maximum clearance is positive. The parts may be either loose or it has to be forced together. So let us part this thought a little bit. Let us go into the interference fit first. So here in interference fit is an opposite condition to the clearance fit. It means that the smallest shaft is going to be larger than the largest hole. That means for this shaft, the smallest most dimension that is allowed is going to be still larger than the largest hole that is possible in the system. So typically it means that you cannot fit the components together using normal condition. that is the maximum allowance is always going to be negative. So that means that there's going to be an interference to it. So here you need to take special manufacturing processes. Suppose that means that you can either heat the component that is going to have this hole so that it becomes enlarged, that is it enlarges greater than this allowance, maximum negative allowance, and wherein this shaft can be fitted in. Alternatively, they can cool this component, this shaft, in order to shrink and then fit it. So typically this interference fits is going to be used in a varying in different automobile components. For example, if you take the gear assembly in your gearbox, there you have your interference fit. Then the wheel hub assembly, there again you have your interference fit. So based on the application, it is going to vary. That is, if the object can rotate freely into it and it's just a transitional element, then a clearance fit can be used. But if there is going to be a strong lock of the relative motion between these two components, then you need to have an interference fit. But that's where you have an intermediate between these two, clearance or interference, that is the transition fit. So it means that the allowance is negative and the maximum clearance is positive. So they can either be as a clearance or as an interference, that is they may be loose or it can be forced together. So it either fits between these two based on the condition that they have. So for these conditions, you can arrive at two different varying parts. That is, if you take in a condition of a minimum of shaft and the maximum of hole, that is, if you see in the largest shaft, that is the max shaft. Okay, let's come here. Yeah, the smaller shaft, the minimum shaft and the max hole. In this condition, if the clearance is going to be maximum, it's going to have a transition fit. Whereas if the interference is going to be minimum, that is the allowance is going to be minimum, that is the negative side, then it's going to be an interference fit. Likewise, this condition where the max shaft and the min hole is considered, if the clearance is going to be, or the interference or the allowance is going to be minimum, then it's a clearance fit. Whereas if there's going to be a maximum interference between these two components, the max shaft and the min hole, then it's going to be a transition fit. So this transition fit, based on the application, you can vary, or it fits between the clearance and the interference fit. So this covers the different types of fit that your sub-assemblies are going to hold. So how do you represent the fits and where to use which fit? Let's look into one by one. So typically this is how you define the fit. So you go for two different types of basis system, that is the hole or the shaft. So for all internal dimension, that is the holes, you have your basic size and then you define the tolerance zones based on it. That is, you define the clearances of the allowances of this by using two denotions. The first is the character, if it's going to be a capital one or a smaller one. So the first letter is going to be your fundamental deviation, that is the position letter, it defines that. Next, based on the numerical system, this defines the tolerance grade based on the fundamental deviation. So then when you assemble these two together, that is, you assemble your hole and the shaft, you go by the base dimension of those two and then define the fit for the hole H8 and for the shaft F7. So what are the types, how it can be defined based on a hole based system? Let's look into. So this is a typical mapping of how it can vary. So this line is going to be a basic size line, and then on this side you have your hole and in this side you have your shaft. So based on that, you go by grouping together of your shaft. So here in hole, for H11 you have to pair up with C11. That means your hole tolerance is going to be H11. So the C11 is going to be your shaft tolerance. So based on this, you define, based on these conditions, you define the maximum most clearance that is available and then minimum most clearance is also available. So based on that, you can see the different nomination, the pairs of nominations that we use to nomenclatures to define the variations. So here until this zone, let me just zoom out. From this zone is going to define your clearance fits, whereas this zone is going to define your interference fit. Wherein here you go for your minimum and maximum interference. So based on this, you select what are the components that you're going to select. And then there's an intermediate zone wherein you can see there's an overlap here. Here it is clearly separated between these two and hence a clearance, wherein here it is going to interfere between these two, that is the shaft is going to be larger than your hole and hence it is positioned here and this is an interference, whereas there's an overlap between these two conditions here, that's going to be a transition field. So let's look into examples to each and every one of it.